A2 Pure Maths, Chapter 11, Numerical Methods. So this is a branch of mathematics called numerical analysis. The idea is it's a method to find solutions where we don't have exact solutions to equations. Obviously, the majority of equations don't have exact solutions, so we're only looking for approximations. We'll be considering the graphs of the functions that we'll be looking at as well, and looking at why we have roots in certain places and whether our approximations are good approximations. So the first section, 11.1, locating roots, a little bit of vocab first. So we've got continuous. So if you look right at the bottom of your notes, continuous interval is one that does not contain any discontinuities. So for example, y equals 1 over x or y equals tan x, you do have asymptotes that are vertical, and therefore you haven't got a continuous graph over that interval. So for this first section where we're looking at a change of sign, we must also have a function that is continuous in the given interval, and that's really important. So first off, show that e x minus 3 equals 0 has a root in the interval 0.5 to 0.6. So all we are going to do, first of all, is if we let f of x equal the function that we're working with, and I'm going to substitute 0.5 and 0.6 in separately, and what we are looking for is a change of sign, and we'll have a look at what is happening with this graphically afterwards. So on your calculator, we're just substituting 0.5 in, plus 2 times 0.5 minus 3. So for 0.5, for f of 0.5, we are getting minus 0.3513 for significant figures, and if we change that to 0.6, we get 0.02211. If I'm going to the same decimal places. So what we've got here is a change of sign. So one of them has come out as positive and one of them has come out as negative. So I've got a positive here and I've got a negative here. So the sign has changed over that interval, and because we know that our graph e of x and the graphs 2x minus 3, even though we might not be able to picture this exactly, if we split it down into those two areas, because basically it is those two functions added together, we know that there are no vertical asymptotes for these functions, therefore we know we're continuous, so we can write our conclusion. So as f of x is continuous and there is a change of sign, let's just move that down here, in the interval that we've been given. So I'm going to use the bracket notation for the interval, which you should have seen when you were doing domain and ranging functions. And we've got a root. As always, show that questions, you must write a conclusion. Okay, so you have to put a conclusion, and it's really, really important when you're doing the conclusion for this that you include both that your function is continuous and that there is a change of sign. So what we mean graphically by a change of sign is if we've got a root, that is just telling us where we cross the x-axis. So that's what root means. So what we've got here graphically is if we were to consider the graph between 0.5 and 0.6, we are crossing the x-axis because we are going from a negative value here to a positive value here, and that's what we mean by a change of sign, which is why it's important that we're continuous over the interval, because if we consider 1 over x as we used as the example before, and we went between minus 1 and 1 as our interval, we would get a change of sign, but we can see that there's no root there because it's not continuous over that interval. The other thing to consider is a change of sign isn't the only way to indicate we have got a root, because it depends what that interval is. So if we consider the graph of y equals x squared minus 1, so x squared minus 1 would look like that. It's a minus 1. And we're looking at the interval minus 2 to 2. So we know that at minus 2, our y value would be 3, and at 2, our y value would also be 3. So we haven't got a change of sign, but actually in that interval, we have got two roots. So you do need to be careful. That's not the only thing that we need to be looking at, and knowing your graphs and just having a quick sketch of what the graph looked like would really help when you're trying to write your conclusions, both for continuity and for looking for a change of sign. Generally, when you're looking at your interval, you'll get quite a small interval that you'll be working with, and the exam question generally set that up for you. So moving on to 1.2. So using the same axes, sketch the graph of y equals ln x and y equals 1 over x. And then we're going to have a look at the equation log of x equals 1 over x and show that it only has one root. So when we're sketching this graph, make sure if you are sketching a graph, quite often you draw really small graphs. The question is asking you to sketch the graph, so make sure you give it a bit of space. So we've got log graphs that looks like that, and obviously you're all up on your graphs because you've learnt them. And then you've got 1 over x graph, which would look like that. It should not be curving up there. It should be making sure it keeps coming down there. So it only has one root because it only has one point of intersection. So that's what we're looking for when we're doing this question. If you think about this bit here, so the log of x equals 1 over x, let's take it back to the AS topic right near the beginning. If you saw a question that said, find the coordinates of a point of intersection, you would do simultaneous equations, and that is all that's happened between these two here and this equation over here. We have equated the y, so we're saying let log of x equal y in here, and we get this equation here. So if we were solving this equation, it's the points of intersection between those two graphs, and because I've only got one point of intersection, that means there's only one root. Remember again, always conclusions. So when we consider B, show that this root lies in the interval 1.7 to 1.8. What you want to do is always make your equation equal to 0, because that allows you to go back to this example here where we're looking for a change of sign. So if you notice, we were equal to 0, and because we were going equal to 0, that means we're looking at where it crosses the x-axis, and it just makes it a little bit easier to show. So if we let f of x equal ln x minus 1 over x, you could also do 1 over x minus ln x, it does not matter. You're then going to do f of 1.7 and f of 1.8. So I'm just going to substitute 1.7 and 1.8 into there, which would give me, for 1.7, I've got minus 0.0576. And for 1.8, I've got 0.0322. Okay. Change of sign again. I've got a positive and a negative. So I can use exactly the same conclusion as what we had before. So there is a change of sign. So f of x is continuous, and there is a change of sign in the interval, and then obviously it depends what interval we're working on. So this time I am working on, notice it is curved brackets, because we're not equal to one curved bracket. So we've got 1.7 to 1.8. Therefore there is a root in this interval, will do. Okay, so you need that as your conclusion. So do watch for that. If we just look at that graphically, so wrong graph, there we go. So we've got y equals ln x is the red graph, y equals 1 over x is the blue graph. I've just zoomed into it slightly there, and we're looking at the interval 1.7 to 1.8. So I'm looking between those two values there. That's where my root is. So when we considered the function that we've just looked at, so ln x minus 1 over x looks like that. What you've got is you've just subtracted the blue graph off the red graph. So where this red graph is big, we're just taking those values off, and it's giving us this black graph here. If you looked at it the other way round, so 1 over x minus ln x, you're not interested in the graphs on either side of this. You're interested between 1.7 and 1.8, and you can see that both of them are crossing in the same place, which is exactly the same solution as what we will get for that point of intersection there. So just to recap, the red graph and the blue graph are the two that we started with at the start of the question, and then you've got this black graph, which is ln x minus 1 over x, or the green graph, which is 1 over x minus ln x. And what it does is it drops those two graphs so that that root that we're looking for, that point of intersection, is actually the point of intersection with the x-axis. So what we've got there is the root is the black line, and you can see that it's intersecting all of those curves in the same place. So we looked at just that one. We did ln x minus 1 over x, which is that point there. So it's just dropped it down to there. So that's what you're doing when you do this bit here in terms of your working out. Okay. I'm going to stop here, so you need to watch the next video to get the next part of this topic.